We move on to the next speaker, who is Jahanur. Jahanur, can you please share your slide?
Can you see my screen?
Yes, yeah, that's perfect. So our next speaker is Sheikh Jahanur Hoque from Charles University. He has been working on physics of de Sitter space, and he will be telling us about surprising consequences of tiny positive cosmological constant in Bondi-Sachs formalism. So what to you, Jahanur?
Yeah, thanks. So I will talk about surprising consequence of a tiny cosmological constant in Bondi-Sachs formalism. And this work is this talk is based on mostly two of my work. And yeah, so let's start with the notion of gravitational wave for asymptotically flat space-time. So for asymptotically flat space-time, there is a well-defined notion of gravitational waves in full nonlinear theory. And this is pioneered by the work of Bondi and his collaborators. So they did a detailed analysis of gravitational waves in full nonlinear theory. And they also provided a definition of energy carried away by an isolated system for gravitational radiation. And this work is a remarkable milestone in the history of gravitational to understand the gravitational radiation in full nonlinear theory. And also Bondi's analysis has found a lot of application in mathematical theory to study the characteristic initial value problem. By characteristic initial value problem, I mean that if you just given a data on a null hypersurface, then you study how this data evolve throughout the space-time using the Einstein equation. And it is also used to study numerical evolution of the space-time. It is also used to study the asymptotic symmetries. And recently it has got some attention on cosmology also. So this is a one slide summary of Bondi's work. So Bondi and his collaborators performed a systematic expansion for axisymmetric gravitational waves along the null direction. Later, Sachs generalized this prescription for non-axisymmetric case. And what Bondi and his collaborator did, so they put a initial data on a null hypersurface, and then you solve the Einstein equation. And from Einstein equation, you will deduce the fall-off for gravitational fields. And as a consequence, as a supplementary condition, you will obtain a mass loss formula. And Bondi introduced a term called News function, which absolute square integrated over a sphere at infinity measures the rate of change of energy loss by an isolated system. By sphere at infinity, I mean you need to go along the null direction, and the sphere is on sky plus. So if you have a gravitating system which is emitting gravitational waves, as presented by this blue line, and you ask what is the energy emitted by the gravitating system, so it is just a nu square, which is this quantity, and integrated on this S2 on sky. And this quantity is nothing but the radiative part of the field. So this is nu is del U of the radiative part of the field, 1 over R part of the field. And I must say that Bondi's all this analysis is highly relied on the fact that the space-time should be asymptotically flat. Now, given the cosmological observations suggest that our universe is accelerating, and which can be modeled simply by a positive cosmological constant. And now, if we ask how to generalize this Bondi's formalism, and how we can extract the asymptotic fall-off condition for the gravitational field, and what are the asymptotic symmetries, and is there an analogous mass loss formula, or is there an analogous News tensor? And surprisingly, this problem remains unsolved for around 60 years. And there are a lot of non-trivialities, and some part of all these things I will discuss in my talk, mostly this first two part, how to generalize the Bondi-Sachs formalism for positive cosmological constant, and how you can extract the asymptotic follow-up condition for gravitational field. And also we will look at the simpler version of this problem. So we will ask the Bondi-Sachs formalism for linearized gravitational fields on de Sitter background. And moving to the next slide. So as I previously mentioned, all these Bondi formalism cannot be generalized from lambda equals to 0 to lambda greater than 0. One of the reason for this non-trivialities is that if you just turn on the cosmological constant, then the global structure of the space-time changes immediately. So actually you can compute the norm of the boundary. Is there any question or?
No, Jahanur.
Okay. So you can actually compute from the conformal Einstein equation the norm of the boundary. Then you can show that this norm is depend on the sign of cosmological constant. So for de Sitter, the norm is time-like. So sky is space-like for de Sitter, and for anti-de Sitter, the norm is space-like. So sky is time-like, and for lambda equals to 0, sky is null. So we will construct Bondi coordinates for de Sitter space-time, and this is the cartoon diagram for Bondi coordinates. So this cylinder is the source wall tube, and the source is emitting gravitational wave along this null direction. So these lines are U equals to constant lines, and Bondi coordinates are based on family of null hypersurface. So these are a family of outgoing null hypersurface, and R increases along this direction, and then del U is along this direction, and the two angular coordinate is transferred to this direction. And as U is the null hypersurface, then the covector of this hypersurface is also null. So if you impose that condition, then you will get this condition. So the small a b runs from all space-time indices in my talk. And this condition actually gives you that GUU contravariant part should be 0. And these two angular coordinate XA, all the capital indices are the usual angular coordinate theta and phi. And two angular coordinates are constant along the null rays. So that gives you this condition. And this implies that GUA contravariant part is 0. Then you can just use the relation between covariant and contravariant metric. Then immediately you can find that these two conditions, GUU contravariant and GUA contravariant is 0, turns out to be GRR covariant and GRA covariant to be 0. Okay. And so in this setup, the GRR covariant and GRA covariant metric is 0. So this is the metric, looks like in Bondi coordinates. So you can see that there is no GRR part and no GRA part from here. And R varies along the null rays. Still, we didn't fix our R coordinate. So we will fix our R coordinate by saying that the determinant of GAB, determinant of the angular part of the metric, is R to the power 4 sine square theta. Or you can think of it like a determinant of gamma AB here should be equals to determinant of a unit sphere. So that's why we just fixed our R coordinate by this determinant condition. And now we want to explore Einstein equation for linearized field, but on de Sitter background. So now if you want to write down de Sitter background metric in Bondi-Sachs coordinate, so it looks like this one. So you have, you just reduce, so you have beta equals to 0 and UA equals to 0, and V has certain, this kind of structure, okay? So for lambda equals to 0, this is just like a Minkowski metric written in U coordinate, U equals to T minus R. Then Bondi gauge condition for linearized fields turns out to be this one, because you can see for the full metric G UR GRR and GRA part is 0, and for the background also GRR and GRA part is 0. So it translates to the Bondi gauge condition for the linearized field, so that HRR and HRA is 0. And this determinant condition actually translates to the condition, the tracelessness of this angular part of the perturbation. And we'll explore linearized Einstein equation with Bondi metric. Okay. Now, if we just plug Bondi's answers, this one, into the Einstein equation, you will get 4 independent hypersurface equation. So the details of the equations are not important, but what is important to realize, Einstein equation in Bondi metric forms a hierarchical partial differential equations. By hierarchical partial differential equations, I mean, so if you look at this equation, the right hand side of this equation only depends on gamma. So given a gamma, you can always solve for the beta. Then if you look at the other equation, EUA, so the right hand side is function of only beta and gamma. So given a gamma, you can extract the beta. Now you know beta and gamma, so you can extract what is your UA. Similarly, for if you look at the equation for V, and this is a function of U, beta, and gamma. So from the previous equation, you already know what is beta, UA. Then you can extract what is V. And I must mention that this function V, beta, and UA are all a function of UR theta phi. Okay.
Janu, sorry, can I ask a small question? So gamma is also gamma also has a 1/r expansion, right? In the way you wrote the Bondi.
Yes. Gamma has also one expansion. Yeah. Then what do we want? We want to linearize all these equations. So in this next line, we linearize all these equation, all this full nonlinear equation. We just linearize it. And from this equation, you can say that this is already in quadratic. So this right hand side should be 0 if you just linearize that. So that translates into that delta beta should be some function of u and xa. Sometimes I use this delta for the metric perturbation also. So delta are similar to h. Then for linearized case, actually you can choose a gauge such that you can set this term, this delta beta, to be 0. So for the linearized theory, you can set HUR to be 0 all over the space-time. Okay, and I think it is also true for lambda equals to 0 case. And then you just look at this equation, and this equation is a little bit non-trivial. So if you look at this equation, so I have the answers for HAB. HAB I have in here. HAB is this quantity. So the answers of HAB is this one. Then we ask how we want to solve this equation. The next equation for UA. Just look at this equation. So the details of this equation is not relevant. So what is important to notice, this equation HUA has a logarithmic term. This comes because of this equation itself, and you also notice that this is a second order differential equation. So it has 2 integration constant. One is HUA 0 and other is HUA minus 3. So for lambda equals to 0 case, you can actually put this HUA equals to 0 as a gauge condition. So you can set this to be 0, but so this HUA minus 3 you will identify with the angular momentum aspect. So for lambda equals to 0, you can set this quantity to be 0 by a gauge transformation. Similarly, you can solve for V. So the point to note is that this HUA term has a logarithmic term, and this logarithmic term depends on HAB minus 2. So this is the next order term to the radiative field. So this is the next order term. Okay. And given an answer HAB, the hypersurface equation, what I have previously shown, this equation actually fix the asymptotic follow-up condition for the other component of the field. So given this free data, you can always fix your other component of the field on a null hypersurface. So now you ask how you evolve your space-time. So this is given by this equation, EAB equals to 0. So previously I have shown that given a free data on this null hypersurface, HAB, and you need to also provide the integration constant. I will come back to the slide also later part of my talk. I will explain this in a little bit more details. So this equation actually tells you how HAB evolves along the del del U direction. So once you have HAB, the hypersurface equation fix all this fall off on this null hypersurface. Then this equation actually tells you what is the value of HAB to a nearby null slice. And you can again get the HAB on this null slice. Then again, you just repeat the previous this hypersurface equation to get the other fall-off condition. Okay. And this is for lambda equals to 0 case, and this is for lambda non-zero case. And now if you look at this equation, what I have shown previously, this EAB equals to 0 equation, and you just ask, I want to study the asymptotics of this equation. You just plug back the HAB answers. So you just plug back the answers for HAB. Then you can just look at this asymptotic analysis of this equation. So the first non-trivial thing you can see that this equation gives you this condition. And this is highly non-trivial because, so you can see from this equation, it implies that HAB minus 2 is 0. And HAB minus 2 appears exactly in this logarithmic contribution. And but for lambda equals to 0, this equation doesn't give any constraint. So for lambda equals to 0, this equation is trivial. Okay. So that means this logarithmic term is not in de Sitter. So the logarithmic terms are absent in de Sitter by the equation of motion itself. And the other way of saying is that de Sitter is non-polyhomogeneous. Usually these expunctions are polyhomogeneous expunction. They are called polyhomogeneous expunctions. And I mean, this condition is completely different for lambda equals to 0 case. For asymptotic flat case, to get rid of all this logarithmic term, you need to impose the condition HAB minus 2 equals to 0 by hand. And if you look at this Bondi's paper, they also doesn't have this HAB minus 2 term. So they just termed it as a outgoing radiation condition. But for de Sitter, it is the consequence of the equation of motion itself. Okay. And I must say that this result is also true for full nonlinear theory. So this work by Compare et al. And also Skenderis. So this absence of logarithmic term in de Sitter is also valid for full nonlinear analysis. Okay.
So, sorry, Jahanur, can I just ask you quickly? So H
sure.
minus 2 is not determined in terms of H minus 1 here in this case, or what is the?
No, I think no.
So H minus 1 is also free independent and H minus 2 is also independent. Is it?
Yes, yes. So that is one non-trivial thing also in this Sitter. I will mention it also in later. I mean, it depends on other fields also.
Okay.
Yeah. Okay. Yeah, so moving to the next slide. So now if you look at again this equation, but to the next to the leading order term, then you will again get a non-trivial equation, which depends on lambda. And this equation is also non-trivial because if you want dynamics in your space-time, say H for the radiative part, HAB minus 1 is non-zero, then you can't put HAB 0 and HUA to be 0 simultaneously by a gauge transformation. But for lambda equals to 0, actually you can put HAB 0 and HUA 0 to be 0 simultaneously by a gauge transformation. But for de Sitter, actually, this equation tells you that you can't put both of HAB0 and HUA0 to be 0 by gauge transformation if you want a dynamics in your space-time. So the statement is that HAB0 and HUA0 cannot be 0 simultaneously by a gauge transformation. So for our purpose, we will set HAB0 to be 0 by gauge transformation. Then we set HUA0 to be non-zero. And you can see that the non-zeroness of HUA0 has a consequence that asymptotic symmetric group of de Sitter is not BMS, because when you study asymptotic symmetries, so you claim that your Bondi gauge is preserved, and you also preserve the follow-up condition for the gravitational field. So now for de Sitter, actually this follow-up condition gets changed. In particular, the follow-up condition for HUA with our gauge, where we choose that HAB0 to be 0. Okay. And whether this gauge is achieved by any physical spacetime, such Kerr spacetime, Kerr de Sitter, or Robinson-Trotman spacetime for lambda greater than 0, it is a little bit difficult. So I must mention a work with Amitav, where we did analysis for Kerr de Sitter spacetime in Bondi-Sachs coordinate, and we have shown that all this equation of motion holds modulo this, but we didn't do the gauge fixing with the boundary gauge fixing HUA and HAB0 term. So, but they all satisfy all the equation modulo this boundary gauge fixing. Okay.
Jahanur, you have 5 minutes to
yeah,
end
sure.
the talk,
I'll
and
just
5 minutes for question answer. Okay.
Yeah, sure. I'll just wrap up. Now, just from this equation here, so we'll derive all the follow-up condition, and then you will see that I have put HAB0 to be 0 by a gauge transformation, and for de Sitter this is 0 from the equation of motion itself, and for our gauge HUA0 is not 0, and you can also derive what is the follow-up condition for the HUU. And just keep in mind that this HUA0 and HUA minus 3 are the integration constant. And similarly, you will get an integration constant if you solve the HUU term, which is this M. And for asymptotically flat spacetime, you can identify this M as mass aspect, and this HUA3 is angular momentum aspect. And for linearized theory, HUR is 0. Okay. Now, yeah, so I said that you have an integration constant M and this HUA minus 3, but now we want to just find how this evolved. Now, if you look at this EUU equation, so this equation gives you how this integration constant M evolved. And also, if you look at EUA equation, so this equation suggests that how the angular momentum aspect evolves. And you see there is a non-trivial term for lambda non-zero case HAB minus 3. So I mean, for lambda non-zero case, only the HAB minus 1 is not the free data. So if you just, I can just go back to this figure. Yeah. So for lambda equals to 0 case, your free data, you can show that only HAB minus 1 is your free data from this equation. So given a HAB minus 1 and this 2 integration constant, you can evolve the space-time on the future direction. But for de Sitter, as you seen previously, the free data is HAB, the other component of HAB also, HAB minus 1, HAB minus 3, and also this M mass aspect, angular momentum aspect. I mean, so this how to identify it as angular aspect, angular momentum aspect, that is a different issue. But also you need to set the boundary condition on the sky. So you need to fix your HUA0 and HAB0. So in our gauge, we have chosen HAB to be 0. So for de Sitter, actually, you need to put boundary condition on sky also to get the evolution of the space-time. Not only you need to put the boundary condition on initial value on the null hypersurface, you need to also put a condition on this future slice of sky. Okay. And this is completely different for lambda equals to 0 case. And I must say that this mass aspect evolution equation must be non-trivial to give some contribution for gravitational memory in cosmological constant. So usually when you compute a quantitative measure of memory is that you just integrate this equation for some initial time ui to uf, then you can see immediately so that there is a lambda dependent term, right? So more precisely, this equation should be computed in the quadratic order. So to look at the energy loss also, but for the purpose of this talk, I just write the linear order of this term. And I'll just summarize that Bondi-Sachs coordinates are constructed for de Sitter, and there is no log term in de Sitter from the equation of motion itself. You don't need to impose it by hand. And the asymptotic follow-up condition for the linearized gravitational field have been obtained in boundary frame, and these are completely qualitatively different for lambda equals to 0 case. And due to different follow-up, the asymptotic symmetry group is not BMS. And a new contribution is expected for memory effect due to cosmological constant. And it will be interesting to generalize this in FLRW case in cosmological space-time. There is a recent work by Bonga and Karthik Prabhu. So maybe we will hear about this in the next talk. Yeah, I will stop here. I will happy to take any questions.
Thanks, Jahanur, for nice talk. Alok has already raised his hand. So Alok, you
Hi, Jahanur. Hi, very nice talk. If you have like a system of particles, then does this log term still vanish? What happens to that equation of motion that you had in the
for the system of particles?
Like suppose you have, I mean, because in flat space, it doesn't vanish.
Yeah, in the flat space, exactly. So it doesn't vanish because of this constraint, right? So I mean, yeah. So
yeah, in flat space, if you have massive particles, then healing is violated, as you know. So you don't. The log term survives. This r cube log r by r cube term survives. So I was wondering here, if you have some massive particles or something, does this equation still give you 0 on the what happens to h minus 2?
I mean, you are taking your space-time to be asymptotically de Sitter or asymptotically
flat? I want to take, but with some sources like particles or something.
Yeah, I think it should hold, right? Because you can think of this HAB2 is generated from some source, right?
Yeah. So
I mean, so
it's always 0. You're saying it's always 0, is it? It's not just.
Yes, I think so, because yeah, you can have some T mu term, but I think this T mu term doesn't affect this contribution.
I see. So the log r by r cube term is always 0, you are saying.
Yeah. So because of exactly the structure of this equation, right?
Yeah. But it's not 0 in flat space.
Yeah, this is not 0 in the flat space. So for flat space, you need to do it by hand. You need to impose that condition.
Well, no, you can't put it to 0 if you're massive particle. It remains.
Okay.
It survives.
Okay.
Yeah. At future.
Okay.
Any further question? We have some time to take up more questions.
So maybe I can ask then one more question. So
yes,
as you said, the symmetry group is not BMS.
Yes.
So I don't know anything about this, but the recent claims in the literature that there's a way to enhance the asymptotic de Sitter group to lambda BMS. I mean.
Yeah. So lambda BMS is not BMS, right? So because of.
But it's not. It's more than it's infinite dimensional, right?
Yes.
It's still dimensional.
Yes, it is still infinite dimensional because of this fact, right? So because this changed the follow-up condition, maybe.
So that is consistent with your analysis. You're saying the lambda.
Yes.
Okay.
Yes.
Okay.
No. Lambda BMS actually they put a different gauge condition. So the compares paper put HUA to be 0, but HAB 0 to be non-zero. I mean, this what I have shown here actually. So you can have a flexibility to choose any kind of gauge right here. At least you can choose one quantity to be 0. So they put this quantity to be 0, HUA to be 0.
So do you know if the asymptotic symmetry group you get with your gauge fixing, is it at least larger than this, and can it be infinite dimension? Even though if you don't know, you may not know the group exactly, whether it's lambda BMS or not, but.
Yeah, so maybe I can just give you one. So I just so the asymptotic symmetry vector should be look like this, and it almost look like flat case, but flat case this xi b should be independent of u. because of this HUA 0 term.
Yes. Yes.
But here this should be this should depend on U.
I see. Okay.
Okay. So because of this fact that HUA 0 is non-zero.
So it's some infinite dimensional group.
Yes.
So much
yes.
larger than BC term.
Yeah.
Okay.
Yeah.
Thank you.
I don't see any further questions. So I had a question related to Alok, but Alokas. So this Xi that just you have shown. So what have you? I mean, computed the algebra or charges corresponding to?
No,
not yet.
we have not computed yet. Yes.
Okay. Okay. So Daud has raised his hand. So Daud, please unmute and go ahead.
Yeah. Hi, Jahanur. I had actually a question which is sort of similar to the question about sources which Alok was mentioning. So suppose you have accelerated sources in d theta. How at all will any of this analysis change? So what I'm trying to see is whether there will be any contribution to the. I mean, you could have accelerated sources in arbitrary space-time, but with an asymptotic d theta structure. So will acceleration of those sources play any role in the radiative fields?
I mean, they will, and mass. I mean, mass loss or some equation may be changed, right? Because if you just consider a T mu nu here on the right hand side, right? You just want to consider a source term T mu nu on the right hand side.
Yes, but with say a delta function source, which is put on an accelerated trajectory. Because in strictly d theta, maybe it is easier to do this computation. Would it have any effect?
Yeah, some equation will get some contribution, but I have not looked at that actually. But I think most of the some equation will change.
Okay. No, I was asking because your construction of Bondi coordinates that seemed to have a natural generalization for. I mean, to retarded kind of it looks like advanced or retarded coordinates which can be set up on any source trajectory.
Yeah, so Bondi coordinates are valid on the far region, right? So it is not valid near the r equals to 0, but you can always construct at near infinity. So when you just study the asymptotics, then it is completely valid. But near the source region, I think Bondi coordinates are not valid itself.
Okay. Maybe I will just.
Can I make a comment?
Right.
Yeah, sure.
Yes, Shyam.
Yeah.
See, you have not put any boundary conditions on the sources. So if you want to talk about asymptotically de Sitter, you'll have to also put some conditions on the stress tensor as it approaches infinity, right? So when you talk about different types of sources and what they do, without those conditions, I don't see how you can ask questions about the asymptotic behavior of the metric itself alone. Your case is presumably only without sources, isn't it?
Yeah. My construction is without source, but for asymptotically de Sitter, you also need to get the follow for the source also. Yes,
exactly. So unless that is specified, so the different types of sources, whether particles or accelerated otherwise, you'll have to say what kind of behavior they have. Only then you can answer that question.
Sorry, can I ask something? I mean, if you have massive sources, you are studying asymptotic behavior at null infinity, right? I mean,
yes.
So you can have particles which go to time like infinity, right? Or I don't know. I'm just asking.
Yeah, but this is already space-like, isn't it? The null infinity is space-like, so all the time-like curves are also going to go there.
But at some point, right? Okay.
Of course, at some point. Not like I0, that's true. You can go anywhere else.
Okay, Amitav, please go ahead with your question.
This discussion is widening. Can I make a remark? Maybe we can close the session and you can be around to continue the discussion. Is that okay?
Yeah, sure.
Yeah, it's okay.
Okay. So maybe you can formally thank the speakers. I mean, the link will be on. Yeah.
Yeah. We should thank all the speakers of this session. So.